All right, hi, welcome. Number 92 ended up being the one that got the most votes by a quite clear majority. Here we go, 92. It says a pulley of moment of inertia 2 kilogram meters squared is mounted on a wall that is shown in the following figure. So there you go, there's the figure. Light strings are wrapped around the two circumferences of the pulley and weights are attached. So light strings basically mean I don't have to worry about the mass of the strings. So typical. What are A, the angular acceleration of the pulley, and B, the linear acceleration of the weights? Assume the following data. R1 is 50 centimeters, there's R1. R2 is 20 centimeters, there's R2. M1 is 1 kilogram, and M2 is 2 kilograms. So, all right, so going to go to my notebook where I have this all set up. And basically, yeah, here's 92. I have all my information that I need. If I were, and I did see this in most of your homeworks, everybody pretty much drew this diagram, which is exactly what you'd want to draw. And then label R1, R2, M1, and M2. So, and we also got the moment of inertia of the whole thing is 2 kilograms meters squared. We're going to need that. And then the masses of each mass is right there as well. So before I get into this, I'm going to draw actually the forces that are acting on this system here. So let's see. Well, I would have essentially a tension force that'd be pulling in this direction. So this is a tension force. I'm just going to call it T instead of Ft for simplicity's sake. So I'll call it T1 because it's a tension force that's attached to the M1 mass. But then I'd also have a tension force here, and I'm going to call that T2 because, you know, right? So that'll be T2 acting right there. Yeah, what the heck? Let's go ahead and do that. Those are the two forces. Those are the two forces that would be generating a torque on this whole thing. So the first thing I'm going to do is do Newton's second law for rotation, making the pulley my object. So if that's the case, I'll have torque net equals I alpha. So torque net, that's the sum of the torques that are acting on my object, on my object. And in this case, I would have a torque from tension 1 and a torque from tension 2. So that'll just be, let's see, which one's positive. So if we go by convention, so that's another thing I'd want to do is that this is just by convention. I don't have to do it this way, but I'll just say that if it's spinning this way or spinning out of the page, that's going to be the positive direction. And then if that's the case, I want to, well, I'll extrapolate all that later. So that'll be the positive direction. No, you know what? I'll do it right now. So if that's the positive direction, I want to keep going, and then that means this is the positive direction for this system here. So that's going to be the positive direction for M1. And then for M2, this would be the positive direction. So again, you could see it all goes up, around, and down, and all of that is the positive direction is what I'm saying. So that means T1 is going to create a torque. If you do the right-hand rule, it'll create a torque coming out of the page. It means it's positive. So it's going to be torque from object 1 minus the torque from object 2 because the torque from object 2 is going to be negative. If you do the right-hand rule, your thumb would point into the page. Or if you just look at it, it's going in the clockwise direction. That's there you go. Equals I alpha. And then any torque is equal to RF sine theta. And so you can see, well, I'd make an R vector. Let's see, I'll do it in a different color, maybe this one. I can make an R vector in this direction. That's essentially R1. It's the same amount as this one. And then I got an R vector. Well, it's pretty much already seen here, but I'll just draw it again anyway. So there's R2. So there's R1, R2. And hopefully you can see both of these. The angle between them is 90 degrees. So I don't need to worry about the sine theta part, or what the heck, I'll write it all in just so you could see it. So I'm plugging in basically RF sine theta for torque 1 and for torque 2. So this is going to be R1. The tension force is the force, so T1 sine theta 1 minus R2 T2 sine theta 2. And for both of these, not 0, the angle is 90 degrees, so sine of 90 is going to be 1. That all equals the moment of inertia times the angular acceleration, and this is what I'm trying to get. So let's see, R1, which they did give me. So it's going to be R1 T1 minus R2 T2 equals I alpha. So I'm looking for alpha. I know the moment of inertia. They gave it to me. Let's see, I know R2. I know R1. They gave those to me. And T2. So T1 and T2 are the only things I don't know. You might be tempted to say, oh, it's going to be the weight of those masses, but that's not true. That would only be true if the masses were at rest. But both of these masses are accelerating. M2, I think is going to be accelerating upward. And then M1 is accelerating downward. And because of that, I cannot be certain that the weight of M1 and or M2 is going to equal their respective tensions. So I have to basically figure out a way to replace T1 and T2. And if I can do that, and then I can get the angular acceleration. And once I got the angular acceleration, it's going to be easy to get the other acceleration. So all this is part A. Okay, so that means then I need to go. So that's using torque net equals I alpha. That's the result I get here. So I can call this equation 1. And that's kind of the relationship I get there. So I need 2 more equations to replace T1 and T2. And basically what I'm going to go to is both these objects, M1 and M2, and I'm going to draw free body diagrams on them and use the second law, just regular old Newton's second law for linear motion. So, okay, let's see what this looks like. So for M1, a free body diagram would be, well, tension 1 pointing up. And then I think it's going to be bigger. So I think I'm going to get M1G like that. And if I'm wrong, if it's not bigger, then the acceleration will be negative, and then I'll just switch the acceleration there. So I got tension 1 pointing up, M1G pointing down. But again, the positive direction is downward for this here. So let's do F net equals MA. This is all for mass 1. So F net equals MA. F net in this case is going to be M1G minus T1, because the positive direction is down, equals the mass times the acceleration. That'd be M1 times the acceleration, which I don't know. And then I'm going to isolate T1 because T1 is what I need to substitute in for equation 1 here. So I'm going to isolate T1. That'll give me M1G minus M1A equals T1. And that'll be, I'll call it equation 2. Next up is for mass 2. Again, a free body diagram. In this case, the tension force is going to be bigger. So we got T2, and then just make that small M2. Oh, wait, that won't. Oh, yeah, it does make sense. Wait. Well, I'm just going to So I got T2, and then this one's going to be smaller because it's going to be accelerating upward, M2G. In this case, the positive direction is upward because, again, I'm just traveling all the way around. So, okay, let's use F net equals MA here. So we got F net equals MA. And then in this case, we're going to be, it's T2 minus M2G equals M2A. Isolating T2. So that's going to give me T2 equals M2A plus M2G. And that is going to be equation 3. So now what I'm going to do here is I'm going to plug in equation 2 and equation 3 into equation 1. So that's my next step here. And that's going to give me, let's kind of make some barriers here. So that's going to give me, use U. So it's going to be R1, and then instead of T1, it's going to be M1G minus M1A. So that's M1G minus M1A minus R2. And then instead of T2, I got this, which is M2A plus M2G equals the moment of inertia times the angular acceleration. Again, that's what I'm solving for. So let's see, what do I know now? Before I go to, like simplifying or extrapolating or anything like that, let's see, what do I got? So I know the moment of inertia. I know M2. I don't know the acceleration. I know G. I know M2. I know R2. I know M1. M1. I know G. I know R1. So I know everything except this acceleration stuff. So I think what I'm going to do is start by replacing, before I even go to simplify and everything, all this A, I know because the pulley spins in such a way that the linear acceleration is going to equal R times the angular acceleration. But R depends on, well, where the rope is with respect to the axis. Because whoa, that was fun. I don't need you anymore. Go away. What? Yes. Get out of here. So R is further away from the axis of rotation. The further you get from the axis of rotation, the greater the angular the linear acceleration is going to be. The angular acceleration, no matter where we go on this disc, no matter where we go on this pulley, the angular acceleration is always going to be the same. But the linear acceleration, A, changes depending on how far away from the axis of rotation we are. So the bigger the axis of rotation, the bigger the linear acceleration. But basically the big idea here is that my angular acceleration is going to be R times the, the linear acceleration is going to be R times the angular acceleration. And I'm going to use that and plug that into here and here. Oh, and these accelerations are different. They're not the same acceleration because M2 is closer to the axis of rotation than M1 is. M1 is further from the axis of rotation. Should have caught that. So this should actually be A1, A1, A2, A2. Make it the same color, A2. Okay? So, and then that means this will be A1, this will be A2, which is good because R is going to be different depending on those things. So, all right, let's plug all this stuff in. We got R1, and then we got M1G minus M1 times R1 times the angular acceleration, which will be the same for no matter what mass we're talking about, minus R2 times M2 times the R2 times the angular acceleration plus M2G equals I times alpha. All right, now I know everything. I know everything except for alpha, but I got alpha on every single one of those terms there. So I basically have to simplify and isolate alpha. And that's basically going to involve a trick where, not a trick, but I'm just going to throw alpha, I'm going to take all the alphas and throw it, any term with alpha in it, throw it on that side. And then I'm going to pull alpha out and then divide by whatever nonsense I've pulled out of. So, okay, here we go. So to start off, I got to distribute these R's. So R is going to go in there and there for R1. And then for R2, it's going to go in there and there. Don't forget that negative, though, that's in there. So this is going to be R1 M1G minus R, well, let's see, that R is going to be squared. So M1 R1 squared times alpha. Gee, that looks like a moment of inertia almost. It's almost like a point mass of a moment of inertia. Okay, sorry, being silly. Okay, and then negative R2 is going to distribute here. So this is going to be M2R2 squared times alpha. And then again, this negative distributes, so it's going to be minus R2M2G equals I alpha. So once again, I mean, let's see. Okay, not done just yet, sorry. So let's now add M1R1 squared alpha to both sides here, and then also plus, oops, didn't want to put in those parentheses. Let's pull them all out. There we go. So the negatives are out there. Okay. So then we'll also add M2R2 squared times alpha, and then I'm also going to add it to this side, plus M1R1 squared times alpha, plus M2R2 squared times alpha. These will cancel, and then these will be left over here. So this will leave me with R1M1G minus R2M2G equals I alpha plus M1R1 squared alpha plus M2R2 squared alpha. All right, so I got alpha here and here and here. So I'm going to pull alpha out. I'm going to pull alpha out and then divide by whatever I have left over. So it's going to be R1M1G minus R2M2G equals the moment of inertia that they gave me of the pulley plus M1R1 squared plus M2R2 squared times alpha. Almost there. And then it's all good from here. So I'm going to divide everything. I'm going to divide everything by all this nonsense. So I'm dividing everything by that. That's what you're going to see next. So it's going to be R1M1G minus R2M2G divided by all that nonsense. And that's going to be my moment of inertia plus M1R1 squared plus M2R2 squared equals my angular acceleration. Plugging everything in, and this is going to be my answer essentially, but I want you to appreciate what it is that we just calculated here. Because that's one of the reasons I did it in algebraic form like this, because essentially what we have for this angular acceleration, well, it's going to be the net torque, and the net torque is, these are the torques provided by, essentially, from the gravitational force here. So it's if I included this whole thing as a system, this is kind of the strange thing here, I would have a torque from the Earth pulling on mass 1, the Earth pulling on mass 2, and then, so that's what that is right there, the external torques on the entire system, and then divided by the moment of inertia of the pulley, plus the moment of inertia of mass 1, which mass 1 is clearly here being treated like a point mass, plus the moment of inertia of mass 2, which once again is being treated like a point mass. And that's essentially the result that I get. Now, if you understand all this enough to skip to this step, more power to you. But again, that makes me very, 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 very nervous. I kind of have to go step by step here to see this result, and then in the end I go, oh yeah, look at that. Because again, there's so many traps you can set for yourself if you just try and skip to this this kind of result here. Plus, I've seen the AP exam. They've basically ask you kind of step by step, just like they usually do. Oh, part A, do this. Part B, do this. Part C, et cetera, et cetera. Okay, so basically though, all I got to do now is plug everything in. So that's going to be, let's see, R1 was 50, yes, 50, but it's going to be 0.5 converting. So 0.5 times M1, which I think was 1 kilogram, times 10 minus R2, which is 20. So that's 0.2 times mass 2, which is, I think, 2. think it was 2 kilograms. Yep, I'm right. So 2 kilograms times 10 divided by moment of inertia, 2 kilograms meters squared. So it's going to be 2 plus m1 again, which is 1, r1, which is 0.5 squared, plus m2, which is 2 kilograms, times r2, which is 0.2 meters squared, equals alpha. So alpha then equals, let me calculate all this really quickly, hopefully. So we got 0.5 minus 0.2 times 2 times 10. It's going to be 1 divided by 0.5 squared plus 2 plus 0.2 squared times 2. 0.43 I'm getting. So 0.43, and it is positive. That means that it is in fact accelerating like this. So it's accelerating out of the page in the positive direction. So and that'd be radians per second squared. That's the angular acceleration of my system. So that's part A. Part B. So part B is not going to be as bad because I'm just going to use the fact that my linear acceleration for A1 is going to be r1 times alpha. So that's going to be, let's see, A1 is going to be r1. R1 is 0.5 times alpha, which is 0.43. So A1 equals, and this is just using the relationship that I got back here for the same reasons that, so if you want to think about this before you do this, you'd be thinking, well, this one should have a greater linear acceleration. M1 should have a greater linear acceleration than M2 because M1 is further away from the axis of rotation. Okay, so let's see if that's the case. Oh, my wife's calling me. Sorry, honey. I'll get back to you. So 0.5 times 0.43, 0.215 meters per second squared. So that's for A1. And then A2, same thing. A2 equals R2 times alpha. So it's going to be A2 equals R2, which is 0.2 times the angular acceleration, 0.43. A2 equals 0.43, almost done, times 0.2 equals 0.086 meters per second squared. Although, yes, it's going in the negative direction though, right? Because we got, let's see, the linear acceleration is going in the positive direction here. Oh, no, it's not. No, it's not. Nope, it's going in the positive direction. Going in the positive direction. My bad. So that's it. There we go. A2 is 0.086 meters per second squared. Yeah, there you are. So once again, basically what I did is I started by making the pulley the object and getting my Newton's second law for rotation, getting as far as I can go, and then using my Newton's second law for linear motion for M1 and M2, and getting as far as I can go to get my replacements, plugging stuff in, and really the rest is just hairy algebra. Hopefully that helped. Let me know if you have any more questions or concerns, and I'll see you guys on Tuesday. Awesome. Thank you. Bye.